So, last time we were talking about flyback circuit, right? I tried to Google it, try to see what is the meaning of a flyback circuit. Anyone tried doing that? Okay. Yeah, I don't know. ChatGPT said that because you store energy in the transformer and then you give it back to the output, that's why it's called flyback. I could not understand. So, yeah, very difficult. But one thing what I've more or less I think I know of is that in fact the flyback converter was there even before these buck converters and boost converters came into picture, right? So it's, although in our story we are starting with buck, boost, and then flyback seems like an advanced topology, but in reality the flyback was there even before, right? And it was actually used to in a way create a very high voltage pulse. So if you see the flyback circuit, right? Yeah, let's say this is the MOSFET. There is of course a magnetizing inductance Lm. So if you see this circuit, if you choose the turns ratio N2 very large, right? And hypothetically even if you don't use this capacitor, right? You turn the switch on, then when you turn it off, this output side you would have very large voltage appearing. If you choose the turns ratio N2 to be very large than N1. We will of course derive the expression also now. And I think so this was used to create a very high voltage pulse at the output. That was some of the initial applications of this, but yeah. So let's start with deriving the input to output voltage. Switch is on, your switch is off. Okay. We have seen, let's call it V1 and let's call this one V2, right? We know V1 by V2 is equals to N1 by N2, and last time we did find out that the inductor current would go up and come down. The voltage across inductor will be, when the switch is on, the voltage across inductor is nothing but equals to V in, right? Where this is your input voltage V in, and when the switch is off, the voltage across inductor is equals to, when switch is off, the voltage across inductor is equals to, switch is off, voltage across inductor is equal to, sorry, when switch is off, the voltage across inductor is equals to, V1 is equals to, V1 is equals to, V1 is equals to, V1, कहाँ सोच रहे हो तुम लोग? V1, okay, minus N1 upon N2 times VO, where this is the output voltage, right? So if we apply the volt second balance now, right, we have drawn the voltage V1, which is the voltage across inductor, so we can apply the volt second balance. So if I apply the volt second balance, which is integral of V1 dt is equals to 0, right, going from 0 to Ts, this would give us the relationship between the input voltage and the output voltage, right. So we can apply volt second across an inductor assuming the circuit is operating at steady state, right. This is something which we have seen already before. So why don't you go ahead, you apply volt second balance. We have drawn the voltage across inductor, right. Go ahead and try to evaluate this integral and see what do you get. Find the expression for output voltage and input voltage starting from integral of B is equals to 0. Sorry? Yeah. You want me to repeat the question? Huh? You have calculated, okay. So what is the answer? N2 by N1 is equals to V0 by Vin is equals to N2 N1 into d1. Okay, good. So Vu by Vn okay, all of you are getting that. So this is of course for continuous conduction mode, right? If you go into discontinuous conduction mode, what do you think? Your output voltage expression would certainly not be the same, right? And from our previous experience we can see that for the same duty cycle your output voltage would be more than what it would be in continuous conduction mode, right? If you go in discontinuous conduction mode. This is what we observed in buck converter also. You can go back, you can check with boost also, you can check with any converter, right? So, but anyways, we are not deriving the discontinuous conduction mode expression now. If you want, you can go back and you can do it. The current will start from 0, go to a peak value, come back and become 0 at gamma times Ts, and then you can do the math and you can try to calculate. Of course, as you understand, this part would remain the same even if it is DCM, right? So of course this part will reduce. So for the average area under this to be equal to 0, if the length reduces of the negative part, the height of the negative part has to increase, and height is nothing but V0. So the voltage will be more if we go to discontinuous conduction mode, right? So you can either derive the expression or you can just have a look at and you understand that the average voltage equals to 0. So the negative part, if it will shrink, the magnitude has to become more so that the average becomes equal to 0, and therefore the output voltage will be more in discontinuous conduction mode as compared to continuous conduction mode. Okay, now let's also draw, let's just capture, let's say, this switch, and now what we want to draw is this switch current and the switch voltage, right? So I want to draw the switch current and the switch voltage with the same axis, since there is no more space in that side of the board. What we will do is we will I can draw it on this side then probably, right? So we need to draw the switch current, the switch voltage. So how would the switch current look like? When the switch is on from 0 to DTS, the switch current would be equals to, sure, IL, there is no current from this winding, there is no current from this winding, right, because secondary diode is open circuit, so there is no current here, there is no current here. So switch current is equals to IL when switch is on, right. So this is your switch current, and then when switch is off, switch current is equals to 0. What about switch voltage? When switch is on, the voltage is equals to 0. When switch is off, then you have turned it off, its voltage is equals to, write the Kirchhoff's voltage law here, right, starting from, let us say, this point. So 0 plus V in minus V1 minus VSW is equals to 0, right. So when switch is off, V in is V in, V1 is equals to minus times N1 by N2 times V0, so it will overall become plus. V switch, you can take it on that side. So it would be a positive quantity whose value would be equals to V in plus N1 by N2 times V naught. Is that okay? So why are we drawing switch current and switch voltages? Because if you have to, let's say, build this circuit, right, you have to, first thing you have to do is you have to go to a market and you have to buy these switch or MOSFET, right? And when you want to buy a MOSFET, what would you convey to the person who is selling you, right? That I want a MOSFET, fine, but there are MOSFETs of enormous number of MOSFETs which are there. So you need to define which MOSFET do you want. Of course, the definition can go in lot many details, but the most basic detail, how would you define a MOSFET, is using the blocking voltage MOSFET or diode or whatever switch you want to buy, right. So the most basic things you would define is blocking voltage, peak current and continuous current. These are the three things which are most basic things with which you would define a MOSFET, right. By looking at these waveforms, now you know what is the blocking voltage. Blocking voltage means when the switch is off, how much voltage it needs to block. For a diode, it would be how much reverse voltage it has to block. So in this case, okay, this is my blocking voltage. Of course, you would not want to have a MOSFET which is just very close to this value, because if there is any sort of spike or something, it might damage the MOSFET. So you would add some buffer over it, right. There are different thumb rules, but usually for a 400 volt application you use a 600 volt MOSFET, for 800 you would use a 1200 volt device. So it's how much, 1.5 times, yeah, roughly about 1.5 times, 1.4 times is the buffer that you add, right. So this gives you the blocking voltage. You add a buffer of about 40-50% over the actual voltage which it would be seeing continuously. Okay. Peak current, from here you understand the value of the peak current, right, which this device would have to sustain while operating in this circuit. Third is what the data sheet calls it is a continuous current, which what it means is how much of continuous current can flow through this device, right, which in this case, because the application does not require a continuous current, right, but understanding that continuous current may be leading to some amount of thermal constraint somewhere. So you usually find the RMS value of this current, and that becomes the continuous current device that you are looking for. So you can calculate the RMS value of this waveform, right. So these things we are not doing RMS definition, all of those things I assume you know, right. So you can find the RMS value of this one, and this is what would feed into the continuous current. So usually the device data sheet would have a value called as continuous current. That means you can continuously flow that current through the device, right. Here the actual current is never continuous, right, it is always an RMS. So assuming that the continuous current limit may be getting derived from the I square R limit, so we usually use the RMS and try to find a device which has more continuous current limit as compared to the RMS of the application that you require. These are of course the first level things, right, the most basic things. Like first is you decide whether you want MOSFET or diode or IGBT or GTO. Second thing is you decide these three things, and then you restrict your search space to few things, right, as you would do. And then now you would, of course you still have thousands of options even with these values. So you would have to further refine your requirement, and now you go into knowing what kind of losses these devices have, what kind of on-state resistances these devices have, what kind of heat dissipation mechanism these devices have, and you go into more details which at this point is not possible for us to get into, but the first level, this is what you would look for when you would select a device for this application. Any question? Yeah, so switching frequency, somebody said switching frequency, right? Yeah. So yeah, of course switching frequency will matter, but if you open a device data sheet, have you seen a MOSFET data sheet? Okay, so once you go back, just Google any MOSFET, TI MOSFET or any MOSFET data sheet, specifically they will not say this is MOSFET is designed for this switching frequency. That you have to decide whether your application, which frequency you want to use the particular MOSFET for, and how do you decide it is based on the losses, right. So that indirectly plays a role here. So that is like level 2, right, not level 1. Level 1 is these 3 basic things in deciding a MOSFET. Since we are talking about, now since we have brought the topic of switching frequency, let me talk a little bit about the losses, and then we will come back to the flyback part, more to be covered there, but let us just talk a little bit more about losses. Okay, just one thing you should observe here before we take it, I remove this diagram, is just focus on this transition and on this transition, right. So this transition and the second transition, this is the first transition is where the device is turning off, from on it is going to an off state. The second transition is where it is going from off state to on state, right. When it is going from on to off, the first transition, in the on state it had some current, in the off state current is 0. In the on state it had 0 voltage, but in, or rather very small voltage, but in the off state it has very large voltage, maybe 400 volt, 500 volt, right. So if you zoom into this transition, right, if you zoom into this transition, you have current, you have voltage across the switch, current through the switch. I am just zooming it, right, in this small part. So there is a switch current and then it becomes equals to 0, and there is a switch voltage which is 0 and it becomes equals to a blocking voltage, right. Think of this time axis is not the same as that time axis, right. This is like the zoomed version of it in terms of x-axis, right. In this case, the way I have drawn it, you see the current becomes 0 and then the voltage becomes, sharply increases. So if you integrate, if you do integral of V switch into I switch into dt, right, what is V switch into I switch into dt? That is nothing but will give you the losses that are happening in the switch, right. If you integrate it on the left side, right, and if you integrate it on the right side, and if you integrate it during the transition, what you get is the losses. So if you see the left side one, there is a current which is flowing, right, voltage is 0, but it is not exactly 0 because switch will have some resistive drop, because the current will flow through its channel, it will flow through the depletion sort of the substrate and so on, right, it will flow through the small wires which are connecting the switch chip inside. So all those small things would add to the resistance. So this is not exactly 0, it's very close to 0 but not exactly 0. So when we integrate, when we use this formula for this region, when the switch is on, right, we call it as conduction losses. So it is just a name for it, essentially it is all integral Vi, nothing else, but we call that as, so if you take a switch, as the name suggests, these are the losses which are happening when the switch is conducting, right. The small voltage drop, for example, if it would have been a diode, let us say 0.7 volt drop of diode, integral of 0.7 into current dt, right. Is that okay? And of course 1 divided by total time period. So is conduction loss clear? Anyone has any doubt in conduction losses? You all know it beforehand? Or at least you get a sense. Any question, any doubt here? So whenever the switch is on, when I switch, it could be a diode, it could be a MOSFET, whenever the switch is on, you will have conduction losses. When the switch is off, right, now focus on this right side part. When the switch is off, your current is 0, you have a voltage. In reality, again, current will not be 0, there will be some small leakage current which would be flowing, right. So even though you have turned off the switch, it is not a mechanical switch, so physically, there is maybe some small leakage current which is still flowing, but the device technologies have matured so much that that leakage current is usually very small, right, and therefore as a power electronics engineer, those values are so small that we do not include in our calculations at all, right, you get the point. There may be some small leakage current, but it is terribly small, we don't include it in the calculation because it will not contribute much to the overall pie. So the losses which are happening when the device is off, in that device we don't account for usually, right. So there is no name for it, there is no space for it, we are not going to put it on the board. Is that okay? There is some loss, anyways this formula would be valid, but the value would come out to be so small that we don't want to account for it. The third loss which is happening here is during the transition. So what is the loss during transition? If you do integral Vi dt, let us say I take this small part, right, delta t whatever, and if I do integral Vi dt 1 upon total time period, what will be the loss contributed by this transition part? What will be the loss contributed by this transition part? Anyone? Anything, I mean you think small, large, infinite, zero, comparable to conduction loss. More than conduction loss, okay. Any other thought? What could be integral Vi dt? If I just integrated over this small period, I am not integrating, this I have done the integration, this big period, this also I have done, this I have neglected anyways, now I am integrating over this small period. Should be, who said small? Okay. More than conduction, small. It's not in saturation, it's in linear region. Anyways, but yeah, sorry, go ahead. Okay. Anyone else understood? Or anyone else wants to contribute anything? What she is saying is right. What she is saying, maybe you explain it once again, little bit slowly. Yeah, correct. So what she is saying is, and this is what I understand, that there will be some phenomena which you are thinking of as an inductor, but actually it is not an inductor, it is a phenomena within the semiconductor device itself because of the capacitances of the device which you are not getting into. But if you really you are zooming into this part, this does not look like this. If it looks like this, then integral is 0, because whenever I switch is equals to 0, right, whenever I switch is equals to 0, V is there, but integral is multiplied, you will get 0. Whenever you are on the left side, you will multiply, you will get a very small value, but this time period is so small that effectively it will also contribute to 0. But in reality, what happens is not this, but this. Okay. So what it means is, first when you want to turn off the switch, the current continues to flow, but its voltage becomes more, right, and then the current becomes slow. So if you now see this period, right, if you see this period, there is large voltage and there is large current. So now if you integrate, even though this period is so small, but because the voltage and the current values are both large, because you have the conduction current few amperes and you have the blocking voltage few hundreds of volt. If you multiply these two, even if the duration is so small, you get a sizable contribution of losses from this part of the whole curve, and we call it, still you can find it using the same formula, and we call it switching losses, because this happens during the process of switching, either turning on the device or turning off the device. So there is an overlap between current and voltage, right. Does not happen that current first becomes 0 and then voltage goes up. No, in fact it will happen the other way around. First the voltage will pick up and then the current will go down. So there is an overlap. So we call it switching losses. This happens, this reverse of it happens when you are turning on the device. Is that okay? Any doubt? How exactly you calculate these, what are the different parameters its effect is, we are not discussing today, but broadly now you understand there are these two types of losses that happen in either a diode or a semiconductor switch, right. In diode, instead of calling it switching losses, we have a different name, we call it reverse recovery losses, right. So in diode we call it reverse recovery loss, but that's in a way nothing but the loss is happening during the switching period, right, because during the switching period you will have a large current as well as large voltage overlapping. So, but in diode we call it as a reverse recovery loss. There is different name, little different phenomena, not for today, but this sort of gives you a broad idea about what is happening in terms of losses in a switch. Any question? Yeah. Good question. Anyone has the answer to her question? The question is, how is the frequency affecting this loss, the switching loss, right? Yeah, well, expensive. Yeah. Okay, so of course switching loss is the integral, right, upon 1 upon T. Now you imagine if you are doing this switching more frequently, right, in 1 second if you only switch 2 times you would have X loss, if you switch it 4 times you will have 2X of the loss, right. So higher number of times you are switching, the loss will directly be proportional to that. So you double the switching frequency, your loss will almost get double, right, and therefore the switching loss of course depends on the frequency. The conduction loss on the other hand still depends on the frequency, but there is no direct relationship, but there is an indirect relationship because you have to find the RMS current to find the conduction loss, and the RMS current would depend on the slope, the inductance value, and which would then indirectly also depend on the frequency, right. But that is more of a derived relationship, but directly if you say yes, switching loss is directly proportional to the switching frequency. Yeah, I cannot explain it again because I have never explained it. I don't intend to explain it also. Yeah, for that we have to do a little bit deep dive into the semiconductor switch. We have to understand how it turns on, how it turns off, what are the different capacitances and so on, which would take maybe at least 2-3 lectures of its own. So we are not going into that, but if you are interested you can of course you can just Google it and read it, or there are some video lectures which are recorded for a little bit advanced power electronics course which you can also go and watch. It's there on YouTube. Not for this basic course. Yeah. Okay, what about losses? So this losses in the switches, there are few more, right. What we are as of now assuming is that gate you just give 5 volt, 15 volt, it will turn on, you remove gate, it will turn off, but in reality from gate also it would consume some amount of current from that 15 volt supply. So there is some amount of losses happening there. So a lot of those small things are there, but these are the two predominant ones when we talk about switches. And then if you see buck converter, you had these two switches and you had an inductor, right. Inductor would also have losses. What kind of losses will be there in inductor? So what are the other losses in the inductor? There is a conduction loss there also, right, I square R. Inductor would be made up of wires, it will have a conduction loss. What else? What are the other losses in inductor? What are the other losses in inductor? Next person. What do you think could be other losses in the inductor? Yeah. Next one. Losses in an inductor. Yes. Magnetizing. But thoda और specific. Person in the front. Next person. Next person. Core losses, yeah. You will have, it's a core, right? It's a transformer. I mean, transformer has a core, inductor also has a core. Your flux is going up and down, up and down. So you would have all sort of core losses, right? What are the different types of core losses? Sorry? क्या मिस कर दिया था? What are the losses in the inductor? Core loss बोला उसने, core loss होता है, तो core loss क्या होता है? What types of core losses are there? Go ahead. Eddy current, correct. दूसरा hysteresis loss, right? So you would have inductor losses, or your inductor or your transformer would have conduction loss, would also have core loss, right? So broadly speaking, these are some of the predominant losses that happen in a power electronic converter. There are so many other losses, but it's just that these are the more dominating ones, right? These are the ones which contribute more to the overall share of losses. Alright, any doubt? Let's come back to the flyback now. Okay, by the way, I just erased the expression, but we got the expression of output voltage is N2 by N1 times D upon 1 minus D. You know buck boost converter expression is D upon 1 minus D. You could have guessed this looks very similar to a buck boost converter with a transformer inserted in between, and that transformer gives you a turns ratio N2 by N1. So now if you want to do an attenuation from 400 volt to 5 volt, you won't stress your duty cycle. Your duty cycle you can still maintain it to be 0.2, 0.3, 0.4, 0.5, whatever, right? You can maintain it in a healthy region, and you can stress more upon the turns ratio, which is like how many turns you want to wind in the transformer, right? So that's why the earlier problems which we saw with buck converter or boost converter in providing a very large attenuation or a very large gain, here it gets addressed by using suitable turns ratio. The effect does not get stressed on the duty cycle. Duty cycle can still be maintained in a very healthy region. The other advantage, so this was of course an advantage with which we started with flyback. The other advantage, and which is like really something you would feel valuable. Let me think of an example here. First of all, okay, you guys have done some robotics or something, right? Few people have done some robotics. All of you have done makerspace course, right? So what did you? That was about a year back now. If you recall, you did this drone thing, right? So that would have some motors, that would have some microcontroller sitting there. Microcontroller would require 3 volt voltage supply for it to operate. You may have some op amps, or maybe some comparator circuits, or maybe some logic circuits which would require 5 volt, or maybe plus minus 12 volt, plus minus 15 volt. So if you see any electronics product, you don't require only 1 volt, you require multiple voltages, and that is true for any product. If you open this air conditioner, for example, internally you would see that there will be so many chips. Some chips would require 3 volts, some may require 5 volts, some may require plus minus 12 volt. So there are basically multiple voltage requirements that exist. Now how do you achieve those? One option is you use a flyback circuit, right? From 400 volt you get 5 volt. Now you can do 5 to 12 boost. You can get 12 volt, you can do buck, you can get 3.3, and then you can try to create. The other way, and which is what is really good about the flyback circuit, is that just one circuit can actually give you multiple outputs. So you just put one more winding like this. This is VO1, this is VO2, this is N2, this is turns ratio N3. Now you get 2 outputs, right? You want one more output, you put one more. So it's the same core where you have one primary and you can have multiple secondaries, right? This is one secondary, this second secondary, you can have a third secondary, you can have as many number of secondary, or you can call it primary, secondary, tertiary, whatever. So basically you can have one primary and then you can have multiple of these, and all of these can give rise to isolated outputs, right? This is isolated from this one, this is isolated from this one, so all of them are isolated, and you can connect theoretically any number of outputs as you want, right? You want 12 volt here, you choose a suitable turns ratio N2 by N1. You want 5 volt here, you choose a suitable turns ratio N3 by N1. So N3 you can control N2, N3 values, and you can get the voltages that you want. Is that okay? No, use it for gain. In fact, I told you, the first application for flyback was actually providing a very large gain. To create a very high output from the battery supply, from 12 volt supply, you create very large output, right? So you use it for high gain as well. Some of the consumer applications you may not see it, but that is anyways there. Even if you see those spark plugs, right? Spark plugs also some of the applications you would find where you would use a small 12 volt supply to create a high voltage spark which ignites the fuel, right? So yeah, there are so many applications where you use it for high gain. Okay, now let's see a little bit how it works, right? For example, if you have 2 outputs, you want a 12 volt here and you want a 5 volt here, and then you want to use it to build your power up your rest of the ICs or circuits. How does it work? So as you understand, the expression would be VO by Vin, or rather the output voltage would be proportional to the turns, right? So if you want 12 volt upon 5 volt, your N2 by N3 turns ratio should be in this fashion, right? Because you only have one duty cycle is common to both of them. So you cannot have different duty cycles. What you can have different is the turns, and that would lead you to different output voltages, correct? How would it work is, when the switch is on, you would still have a current flowing in the inductor. When the switch is off, now the question is, will the current will still circulate in the primary? On the secondary, the current has two options, it can flow through this diode or it can flow through this diode. Which one would it choose? Will it choose this diode or will it choose this diode? So how it works is, let's say this you want to be 12 volt, you have designed the turns ratio based on that. Actually, somehow this voltage drops to 9 volts, hypothetically. So suddenly what will happen is, this diode will get forward bias and all the current will flow here, and this diode will remain reverse bias. If it gets forward bias, let's say this is 9 volts, so 9 volt will appear here. So the voltage that would appear here is 9 times N3 by N2. And what is N3 by N2? N3 by N2 is 5 by 12. So if you do 9 multiplied by 5 by 12, what will you get? You will get something less than 5. If you get something less than 5, this diode will be reverse bias, right? This is very similar to common cathode configuration, but it's a little bit different picture, but it's the same principle. Basically, there are two diodes. Output side you have some voltages, input side they have, in this case they don't have common voltages, but there is a turns ratio, so common cathode configuration. So whichever output will be less than the desired value, that diode will conduct, shoot it up, bring it to 12 volt. Once it is 12 volt, then both diodes may conduct simultaneously. If one of the voltage drops suddenly, 5 volt goes to 3 volt, then again majority of the current will start flowing into that output, it will bring it up, and then it will try to maintain both of them. Okay, which part should I repeat? All of it? Okay. So now, okay, let's take this example. So 12 volt is here, 5 volt is here, right? Turns ratio you have decided based on the nominal voltages that you want, 12 and 5, okay? Now here, instead of 12 volt, I have, let's say, suddenly increase the resistance, suddenly reduce the resistance. So I have suddenly tried to draw a lot of current. Now the sudden current will be supplied by this cap, it will lose its energy, so this voltage may come to 9 volt, okay? Now this has become 9 volt, the circuit is still operating. If this is 9 volt, let's assume that diode D1 conducts. If diode D1 conducts when the switch is off, then what will be V2? V2 will be equals to minus 9 volt, is that okay? V2 will be equals to minus 9 volt. So what will be V3? V3 will be equals to, V3 by V2 is equals to N3 by N2, right? So V3 will be equals to minus 9 multiplied by 5 by 12. How much is that? Can someone quickly calculate? 3.75, okay. So if you solve it, you get V3 is equals to minus 3.75 volt, okay. Now what is the voltage across the diode? Voltage across the diode is, this is minus 3.75, so 3.75 minus 5, so voltage across the diode will be negative 1.25 and the diode D2 will be reverse bias, right. So if the voltage is suddenly dropped, this circuit automatically will push more current into that side, and now all the current is flowing here when the switch is off. Again when the switch turns on, the current will build, again when switch turns off, all the current will go here, nothing will go here. So this voltage will automatically go up, right. Once it comes closer to 12 volt and this is 5 volt, then both the diodes can conduct together, right. Suddenly later on when one of them goes down, again more of the current will start flowing into that and it will bring it up. So this is a circuit which can which is very good if you really want multiple outputs. It has this sort of natural instincts of balancing the voltages. Of course, there are still a lot of practical challenges, but at least at first cut level, it looks a very attractive solution instead of using so many buck converters or boost converters to generate multiple voltages. It's possible with lower voltage also, same thing, 5 volt goes to 4 volt, right. Assume this diode conducts, this becomes 4 volt, you find this voltage here, you will get 11 volt, this diode will be reverse bias, so everything will flow here. Yeah, you can do that, okay, good. You guys know a lot of things, very nice. So what he is saying is, why don't you on the secondary, instead of using 2 windings, you use something like a center tapped. You can get 12 volt here, you can get 5 volt here, sure, why not, yeah. You can do this also, if you don't, as of now not able to understand, that's fine. I have done nothing, right, I have just stitched the 2 circuit. This diode I have bought it in the bottom and then I have just connected the 2 circuit, I have done nothing else. So this would, with respect to a common output ground, it would give me plus 12 volt and it would give me minus 5 volt. So if your applications require both plus and minus voltages together, then you can use a circuit like this. You can get plus 12, minus 12 to bias your op amp, for example, right. It's the same circuit, I have just connected them together. So you can connect like this, or physically what you can do is you can connect this output to this one and ground it, and you will get now plus 12 and you will get here minus 5 volt. So it's one and the same thing, right, it's one and the same thing. You still require those number of turns, it's just that how you connect the 2 turns, so you can represent it the way it is shown in left side, or you can represent it the way it's shown in the middle one. Okay, any more questions? At steady state, yes, maybe not necessarily during transient, but at steady state, VO1 you can write it as N2 by N1 times D upon 1 minus D. Correct. So when we are saying we are operating at steady state, means this is also 12, this is also 5, right? And when these 2 turns, when the switch turns off, both the diode conducts. So you can either calculate VO1 as N2 by N1 times D upon 1 minus D, or you can calculate VO2 as N2 by N1 times. So the assumption itself we are taking is these voltages are proportional to the turns ratio. Any question? Okay. So as you can see, this is like really good. I mean, you can use it a lot of places, quite popular. This is a basic flyback circuit, but there are more advanced flyback circuits also. But there is little bit of flaw or little bit of limitations here as well. Now question is, what is that limitation? Can anyone point out? Okay. 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 Yeah, but in reality transformer would always be non-ideal, right? In fact, getting an ideal transformer would figure a bigger pain than actually just a regular transformer. LM would actually be very high, na? Ideal transformer LM is infinite. You mean the other way around. LM may not be very small. Okay. So he is saying the problem with flyback is that this LM is part of the transformer, right? Usually the transformer would have very large value of LM, so the current will not build up, right? If current doesn't build up, you will not be able to transfer much energy output. So actually you would require a smaller LM, so that current builds up and then there is more energy stored, it can be transferred to the output. Is that okay? Not okay? You want me to repeat what he just said? How many of you understood what he just said? Please raise your hand. Okay, how many of you did not understand? 1, 2, 3, 4, 5, 6, okay. Now do we have, okay, we don't have those waveforms, but let's just say this one, yeah. So for you to transfer energy, you are storing energy in this transformer and then you are giving it to the output, okay. How much energy gets stored in the transformer depends on the peak current value, right. If the inductance Lm is infinite, yeah, if I close the switch, if this is infinite, what will be the current flowing through the switch or the inductor? Current will be 0, right. So no energy will be able to get stored in the inductor itself, so nothing will get transferred, right. In reality, whenever you take transformers, you would want to have larger Lm value, right, which is closer to the ideal transformer. In reality, never ideal, but closer to the ideal. So if Lm is large, the energy transfer would be small, right. So naturally this circuit may not be good enough or may not be suitable to transfer large amount of power from input to output. That's what he is saying. Is that okay? Yeah. Is that okay? Any question? Any other argument? Could add an extra inductor, okay, so let this Lm be there. I will just take a core, I will put a few turns, I will make one more Lm prime, I will add it with the transformer and extra inductor, and that should be able to overcome the problem we just talked about, right. Yeah, because now you are not using the inherent transformer inductor, it is also contributing little bit, but you can add an inductor external, you can design it to be the value you want it to be, right. So unfortunately nothing bad with the circuit then. Yeah, but here first of all you are getting an opportunity to get 2 voltages, was not even there in buck converter, right. So firstly you should be thankful to this guy. Yeah, nobody is perfect, right. So this guy is also not perfect, but still does a better job than just a buck converter. But any other problem? But you are correct, you are absolutely correct that yes, if one of the voltage drops, it would also have impact on the other voltage. And there is a term for it, we call it cross regulation. Again, you know, something which we can later on see, if you want to search it, you can search it, cross regulation, right. Any basic problem? We want to move to a new circuit, we must find a problem here before we move to a new circuit. Okay, some of you tried googling problem with flyback converter? No, maybe you are searching for something more interesting. Okay. Maybe let's try that, right? Can one of you just ask some ChatGPT or whatever, Copilot or anything? What is the problem with flyback converter? Let's just see what comes out of it. Search kare. What is the problem or what are the limitations of flyback converter? Somebody can search what is the problem with flyback converter. Somebody can search why flyback converter is not used in high power. Just try different searches, let's see what you get. Okay. Excessive ripple voltage on the output, okay, that's a good one, I could not have thought of. Okay, any other problem? Of course, one problem we saw, which is the large Lm leading to small energy transfer. Anything else? Any new point you found? Saturation of the inductor transformer, yeah, inductor will saturate, transformer will saturate in our next topology also. So I won't put it for now because you would still have to live with transformer, right? There is no, you cannot avoid it. Yeah, maybe. The other guy may also saturate high voltage. Very difficult to compare, difficult to clearly say because unless we see the next circuit, very difficult to say whether in that particular aspect it is bad or not. Anything else? Any other points? That this guy also said, right? So, but that's only if you have output voltage, so let's not put it as a negative thing because anything else? Voltage spike on the switch happens in all the circuits. right? Voltage spike in the switch, we have not discussed it, but it happens with all the circuits, and there are ways to mitigate it. Yes, you use a snubber circuit here if you go in more details, but that doesn't mean the other circuits they will also have similar problems, one way or the other. Any other thing? Okay, so then let me ask you a different question, which will probably answer these things. You know buck converter, right? Buck converter you know, boost converter you know. All of you know buck boost converter? How many of you know buck boost converter? Buck boost? Almost सबको पता है? ठीक है. Now the question is that I have a 50 volt battery and I want a 100 volt output. 50 volt battery, 100 volt output. Which converter should I choose? 50 to 100. Which converter should I choose? Forget about flyback, huh? Don't say flyback. Among the three, which one should I choose? Boost or buck boost? Look, buck boost can do it. Why do you want to choose boost? Why do you want to choose boost? Buck boost can do it, right? Sorry? Oh, there is another buck boost which doesn't give negative output. I'll ask you in the quiz. Huh? But there is another buck boost circuit which doesn't give negative output. Boost will have higher D and that is more desirable. क्या बोल रहा है? Higher D, boost is not most desirable because as the D increases, your losses becomes more in fact in boost converter. This is what we saw. Huh? Maybe you are saying the other way around probably. Huh? Yeah, so you would not use buck boost, you would use boost, right? If you want to buck the voltage, you would use a buck converter, you would not use a buck boost converter. You would only use a buck boost converter where the input is fluctuating or the output is fluctuating, so that with the same circuit sometimes it has to buck, sometimes it has to boost, right? But why is that? They may require same number of switches, they may require the same number of inductors, same number of capacitors, but you still do that because to go from 200 to 400, right, the ripple in the inductor current is going to be smaller if you are using a simple boost than a buck boost. The ripple in the input current drawn would be smaller in case of a boost because in boost you have a inductor connected at the input, right? In buck you have inductor connected at the output. So if you use a buck or a boost, at least either the input ripple or the output ripples are smaller. If you use buck boost, both input ripple and output ripple both are very, very large, right? Shall I draw the circuits quickly so that you can correlate with what I am saying? Assume we are using very large inductor, right? This is boost. So if very large inductor means this current will be almost constant. So the input current ripple will almost be 0. Barabar? The output current ripple will still be there. If I use a buck converter, one second, if I use a buck converter, then my output current ripple will be almost 0, right? The input will be there. Output current ripple, the current ripple going into the capacitor is almost 0, right? So even a smallest value of capacitor would work out to be fine for you. If you see the buck boost, even if you use a large capacitor, your input current ripple will be substantial. You can draw the waveforms. Even if you use a large capacitor, your output ripple will also be substantial. Correct? So if you see in terms of the overall efficiency and the overall inductance usability, these circuits are better than buck boost. The only problem is these guys can only do one at a time. They cannot do both the things, right? So if your choice is that always have to boost, you go with buck boost. You don't go with you go with boost. You don't go with buck boost. And that's the same reason. If you remember, the flyback is like a buck boost circuit, right? If you always want to can operate in boost, or you can always operate in buck, you should not use flyback then. You can use some other topology, right? So we move to something called as a forward converter. Okay, which is actually a buck derived topology. It's a buck derived topology. So it has inductor, it has an inductor at the output, and what it does is this, because this inductor is at the output, you can use a very small output capacitor to maintain a small ripple. You don't need a large capacitor. On the other hand, in flyback you require a large output capacitor to maintain a small ripple. Is that okay? Buck derived, and therefore small output voltage ripple. Alright, of course it does require a little bit more components, right, which we will see. You guys know forward converter, na? Yes? No? No? Okay. It requires more components, which we will see, but still we go for it because of this advantage. And finally it is all about, cost in a way. So if you are building very small thing, for example the mobile phone charger, right, you would like to minimize the number of components, you would say let us use flyback, just one transformer, one switch, one diode, life is done. But if you are building some high power system, then cost of the capacitors and everything will start mattering. You won't mind increasing the components as long as the sum of the total cost is lower. So that is the reason, it's not like A is always better than B, it depends on your application, on your situation. How it usually spans out it for lower power, usually flyback works out to be very, very well. As you increase the power, slowly you shift from flyback to forward, and then you shift from forward to few other circuit topologies, whichever is more economical to operate. Let us draw the forward converter now. Again, don't ask me why it's named forward converter, but you would get a sense why it's called as forward converter at least. Okay, so far very, very similar, still very, very similar, still very similar, and now all the changes. So we still have to use inductor somehow. You can see why I called it as a buck derived, because if you just look at this circuit, it looks like a buck converter, right? If you just look at this circuit, it looks like a buck converter at the output stage. Now instead of having a source here and a switch here, I have added like a transformer based circuit, so that it operates with a like you can utilize the gain ratio of the transformer. Any doubt? I mean, of course you should have doubt how it operates, which is something which we can cover in the next class. So we will not go and start drawing the waveforms, but is the motivation clear to sort of move on to the next circuit? Unlike flyback, so flyback is actually really, really good, right? You would find a lot of applications around you, you can see things, even any electronic board you would open the board may have so many things, there may be a small flyback sitting somewhere there, right? Forward is not a very common circuit, not as common, but it's very important, because this changes the whole principle of operation going from the flyback, because flyback you are using the magnetizing inductance itself. Now here you have a separate inductor and you have a separate transformer, right? So you would not find it, I mean at least I cannot think of an example, but this is important because this gives rise to so many other circuits which you would see around you, especially for higher power applications, right? So I think let's, any question? Yeah. What made it better than the buck converter is small output voltage ripple, right? In fact, better efficiency also. What doesn't make it better from a what doesn't make it better from a flyback is more number of components, which you may not want if you especially building any low power system, right? Any doubt, any question? Why does it have? Why does it have better efficiency is because it sort of goes back, and if you compare a boost with a buck boost for the same output power, right, you would get a better efficiency if you use a boost than a buck boost. I will give you an example. Let's say I want you to create 400 volt output from a 350 volt supply. So if you use a regular boost, you have to boost only 50 volt, right, 350 to 400. If you use a buck boost, practically 350 all energy dumping into inductor and then transferring to 400. So that's, you can, of course you need to derive a detailed equation, but broadly speaking your 400 volt 350 to 400 would have come out to be more efficient using a simple boost than a buck boost. So same thing here, instead of using a buck boost, just using a dedicated buck or a dedicated boost could give you, it has more potential of giving you better efficiency. Finally, it is of course all about money, right? You can put wires made up of gold and then you would get a better efficiency, nobody can stop you. But if you do a more practical comparison, then it's the same basic principle, because boost versus buck boost. You should all go back and try to search boost versus buck boost.